what we've been doing so far is looking at how to write numbers in binary, but we've only been looking at whole numbers and whole negative numbers. So for instance, we have a pretty good idea now of how we could write, say, 20 in binary, or -5, or -6. So we've looked at a few different ways to write negative numbers in binary, and we've looked at how to write whole numbers in binary, so 18. What if we have a number that's too large for our bit pattern? So for instance, the max value for an 8-bit number is 255, and this is assuming we're not doing negative numbers. So for doing positive numbers, the maximum number that we can store in 8 bits is 255. So let's say we have a system that we can only do 8-bit numbers, and so the max number we can do is 255. Well, what if we have 300? How would we store that? Well, that seems like that would be a problem because we can't store a number that large. So that's where floating point notation comes in. Floating point notation allows us to store integers that are larger than the maximum value that can be held by a bit pattern. So for instance, we could store a 300 if we only had 8 bits available. Usually you'll see this when people talk about larger numbers. Usually they're talking about really large numbers, like maybe 3.5 times 10 to the 20th, or 3.5 times 10 to the 8th. So these are like really large numbers. So floating point notation can also be used to represent real numbers. So let's say we have 3/4 or square root of 2, or let's say we have an infinitely repeating number, so 0.333333, or pi, like pi is 3.14159, and it's an infinitely repeating number. What about 0.125? So we've seen ways to represent whole numbers, but we haven't seen a way yet to represent these fractional numbers. And so real numbers encompass whole numbers and fractional numbers, and basically all numbers except for irrational numbers and infinity. So floating point notation is used to represent pretty much everything else except for smaller whole numbers that you might not use floating point to represent. And that'll make more sense when we get into variable types and how to figure out your different variable types. But what you need to know about floating point notation is that it's used to represent integers that are larger than the maximum value that can be held by a bit pattern. So for instance, if we had 8 bits, a number larger than 255, and they can be used to represent real numbers, so fractional numbers. So we need to go back in order to write numbers in floating point notation. We need to go back and review scientific, and I'm going to change this to and normalized number representation. And the reason why is because floating point notation is based on scientific and normalized number representation. So with scientific notation, let's just put this number into scientific notation. So we have 435,000,000. We want to write this number in scientific notation. So what we do is, first of all, figure out where we want to put the decimal. Usually you put the decimal between the first and second digits. So we want to put the decimal right here. So what I'm going to do is first write 4.35 times 10 to, and then I need to figure out what goes here, like what exponent goes here. So the way I get that is I put the I'm going to add a decimal to the end of the number since it doesn't have a decimal already. And then I'm just going to count over. So 1, 2, 3, 4, 5, 6, 7, 8. So that means that this is 4.35 times 10 to the 8th. So this is what's referred to as scientific notation. And this 4.35 is called the Mantissa. And this 8 is the exponent. So this terminology will be important when we get into the floating point numbers, because you're going to need to know what the mantissa is and what the exponent is. So you also see numbers written in this normalized notation. Normalizing, like if with this one it's normalized to 1. So I'm just going to move the decimal one more spot. So if I go back up to this number, I'm moving the decimal to in front of the 4 instead of between the 4 and 3. So I get 0.435 times 10 to the 9th. And the reason why that's 9th is because if I go back to here, 1, 2, 3, 4, 5, 6, 7, 8, 9. So for this number, this would be the 0.435 would be the mantissa, and this 9 would be the exponent. So let's, in order to use the floating point notation, we need to know how to write binary numbers in scientific notation. So what we've done here is write decimal numbers in scientific notation, but we want to know how to write a binary number in scientific notation. So we're going to learn a couple things from this that we haven't learned yet. So we have this number 567.125, and we want to write this number in first binary, and then we want to put that binary number into scientific notation. So we've been seeing a lot of binary numbers, and you might wonder, well, how in the world do we get the decimal number into a binary number? How do I know what 9 is in binary, or 8 or 7, or some of the numbers we've already been using? So the way that we do this is, first of all, so if we go to this number, so the 567.125, I'm going to look at this number as two separate parts. I'm going to first do the 160 or the 567. I'm going to put the 567 in binary, and then I'm going to put the 0.125 into binary, and then we can combine them. So let's start with the 567. So I'm going to start 567, and all I'm going to do is divide the 567 by 2. So if I do that, 567 divided by 2 is 283.5. And so if I get a 0.5 here, I'm going to put a 1. And what this is this, I'm just actually going to say A0 is equal to 1. So that's the bit that, this is the bit for the spot. So A0 is equal to 1. So now I'm going to take the 283, so 283, and divide that by 2. And so 283 divided by 2 is 141, 141.5. I have a 0.5 again, so I'm going to say that A1 is equal to 1. Now I'm going to take the 141 divided by 2, and this is equal to 70.5. I have a 0.5 again, so I'm going to say that this A2 is equal to 1. Now I'm going to take the 70 divided by 2. So 70 divided by 2 is 35. So I have 35.0. Okay, so now this one's a little bit different because now I have a 0 here instead of a 5. So now I'm going to say that this bit is equal to 0. So basically if I have a 0.5, I'm going to say that bit's equal to 1. If I get a 0, I'm going to say that bit's equal to 0. Now I need 35 divided by 2. This is equal to 17.5. And A4, so I have a 0.5 here, so A4 is equal to 1. 17, now I'm going to take the 17 divided by 2. That's equal to 8.5. And so A5 is equal to 1. So I'm saying that this is equal to 1 because I have a 0.5. Now I'm going to take this 8 divided by 2. So I have 4.0. And I have a 0 here, so A6 is equal to 0. Now I'm going to take this 4 and divide it by 2. So I'm taking this 4, dividing by 2. I get 2. So I have a 0 here, so A7 is equal to 0. Now I'm going to take this 2 and divide by 2. So 2 divided by 2 is equal to 1.0. And I have a 0 here, so A8 is equal to 0. And now I'm going to take this 1, so 1 divided by 2, 1 divided by 2 is equal to 0.5. And so now I have a 0.5 here, and so I'm going to put A9 is equal to 1. And I'm going to stop here because I have a 0 here. So you stop when your quotient integer becomes a 0. So we've gone down, this is our quotient integer, and we divide by 2, and we keep doing this until it's equal to 0, and then we're done. So now we can write our binary number. So if we put our bits in order, A9 is the most significant bit. So I have A9, A8, A7, A6, A5, A4, A3, A2, A1, and A0. And now I can just plug in now I can just write down the numbers that I got for these. So 567, and I'll put that this is base 10, in binary is equal to 1, 0, 0, 0. So 1, 0, 0, 0, 1, 1, 0, 1, 1, 1. And I'm going to specify that this is base 2 or binary. So this is our binary number, and we can verify this. So I'm just going to put the digits here. So 3, 4, 5, 6, 7, 8, 9. And so we can verify that this is correct if we do 2 to the 9th plus, because we have a 1 by the 9, and we have a 1 by the 5, 4, 2, 1, and 0. So I'm going to do 2 to the 5th plus 2 to the 4th plus 2 squared plus 2, 1, 2 to the 0, and this should equal 567. So if you want to go ahead and verify that, but this is the binary number for 567. So we have our number for 567, and I'm going to go to the next page and rewrite the 567 base 10, and this is equal to 1, 0, 0, 0, 1, 1, 0, 1, 1, 1, and I'm going to specify that this is the binary or base 2. So now what we need to do, so we have the 567, now we need to put the 0.125 in binary. So 0.125, and we're going to write this in binary. So the method for this is a little bit different from the method for the whole number. So what we're going to do instead of dividing by 2 is we're going to multiply by 2. So what I'm going to do is take 0.125 multiplied by 2, and this is equal to 0.25. And this is going to be the A -1 bit is equal to 0. And so the way the bit pattern is, so remember we had A9, remember we had A9, A8, A7, A6, A5, A4, A3, 2, 1, 0. And then we have point A, -1, A, -2, A, -3, and so on. So for this number, for the 0.125, the A, -1 is equal to 0. And the reason why that's equal to 0 is because this number is 0. So now let's take the 0.25 and multiply that by 2. So 0.25 multiplied by 2 is equal to 0.5. We have a 0 here again, so A, -2 is equal to 0. Now we're going to take the 0.5 and multiply it by 2. This is equal to 1.0. And now we have a 1 here, so the A, -3 is equal to 1. And the way we're going to do this is you're going to keep multiplying by 2 until the fractional part becomes 0, so until this becomes 0, or until you have enough accuracy. So if you have a number that repeats forever, you're never going to get a 0 there, but you're going to notice that you start getting a repeating pattern. And so once you have enough accuracy in your number, you'll stop. So now what we can do is we can write our fractional number. So 0.125 is equal to, and I'm going to specify that this is base 10. This is equal to 0.001, so 0.001 in binary or base 2. And so now what we're going to do is just put the number together. So we have the 567.125 base 10 is equal to 1,000,110,111 point, so this was our 567 point, 125 is 001, and this is base 2 or binary. So we've now written our number in binary. Now what we need to do is put it in scientific notation. So what we're going to do is, so we looked at the scientific notation for base 10, and so we have so for instance, to put this number, this 435 million, to put this into scientific notation, we just put a decimal in and counted over. So we counted, 8, so 4.35 times 10 to the 8th. So we're going to do a really similar thing for the binary number. The only difference is we're going to have a times 2. So we're using base 2, so we're going to have a times 2 instead of a times 10. So our mantissa will go here, and our exponent will go here. So let's first of all figure out what our mantissa is. Usually we want to put the decimal between the first and second number, so we're going to put our decimal here. So that means that our mantissa is going to be 1.0001101111001. So let's write that. So 1.00011111001, and then we have times 2 because it's binary or base 10. And now we need to figure out what the exponent is. So all we're going to do is move our radix point. So we're going to take the radix point and move it over. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So that means that our exponent is 9. So this is our this is 567.125 in binary and scientific notation. So this is scientific notation. So this is the scientific notation. This could also be written in normalized notation. So to write this in normalized notation, we move the decimal one more spot. So like that. So this would be 0.1000110111001 times 2 to the 10th. So this one is normalized notation. All right. So now we've seen how to write a number, both a whole number and a fractional part, in binary, and then how to convert that into scientific notation. So now what we want to do is look at specifically how the floating point notation works. So let's look at 8-bit floating point notation. So what we have, first of all, we have our sign bit, and the sign bit is what tells us the sign of the number. So for instance, if the sign bit is a 0, we have a positive number, and if the sign bit is a 1, we have a negative number. And the next 3 bits, so A4 through A6, are and this is for the 8-bit floating point notation, so A4 through A6 are the exponent bits. So the exponent bits are the bits that we're going to use to represent the exponent. And this is written in excess 4 notation. So remember, we looked at the excess 8 notation before, and remember what that meant was we added 8 to our number and then we converted it to binary. So with the excess 4 notation, all we're doing is adding 4 to our number, and then we're converting it to binary. And then the A0 through A3 are the Mantissa bits. So these are the bits that will represent the Mantissa of our number that's in scientific notation. So let's look at an example of this. We want to know what is the decimal value of 01111001. And we're assuming that this number is written in the 8-bit floating point notation. So what we want to do is, what I usually do if I have a floating point number is I split it into the different components, so the different bits. So first of all, I have the sign bit, I have the exponent bits, and I have the Mantissa bits. So I'm just going to write down the values that are in each of these bits. So first of all, I have a 0 in the sign bit, and I have 3 1s in the exponent bit, and then I have 1001 in the Mantissa. So right away we can tell that this is a positive floating point number because we have a 0 in the sign bit. So if we have a 0 in the sign bit, that means that it's positive. Now let's look at the exponent. Well, actually, let's write down, so this part of the number is our Mantissa. So going back to the scientific notation, we know that our number is written as the Mantissa times 2 to the exponent. So before I write this Mantissa, let's go back and look at how numbers can be written in floating point notation. So remember, we have the scientific notation, which was here for this binary number. So we have 1.0001101111001 times 2 to the 9th. So that means that this is the Mantissa. And with the normalized notation, we have 0.10001 1, 0, 0, 0, 1, 1, 0, 1, 1, 1, 0, 0, 1. So this part of the number is our mantissa. So when numbers are put into floating point notation, and it doesn't specify for this problem if our number is entered into, if we go back to this 8-bit floating point number, this hasn't specified if our mantissa is written with the scientific notation or the normalized notation. So usually with floating point numbers, like let's look at this number. So 1.000 110 111 001. So this is our mantissa. So if a binary number is written in scientific notation, we can assume that this value, this number to the left of the radix point, is always going to be 1 if it's written in scientific notation. So if this number is always 1, we don't actually need to put that 1 into the so when we put this number into, when we put this mantissa into our floating point notation, we don't actually need to put this 1 in, because we can assume that that 1 is already there. So then what we put into the mantissa is actually just the numbers to the right of the decimal, and then we're assuming that the number to the left of the decimal is always 1. So if I go back to this number, if I go by that, like if I assume that this floating point number is, this mantissa was put in to this number in scientific notation, and that I'm assuming that there's a 1 to the left of the decimal point, then that means that this would be 1.1001 for the mantissa. Now we want to figure out the exponent. So our exponent is 111. So, but it's written in excess4 notation. So what we need to do is figure out what this binary number is, the 111, and then once we figure out what it is, we subtract 4. So 111, I have 0, 1, 2, so 2 squared plus 2 to the 1 plus 2 to the 0. This is equal to 7. And now I need to subtract 4 because I have the excess 4 notation. So 7 minus 4 is equal to 3. So that means that the exponent is equal to 3. So this is what our number is in scientific notation. So now what we can do is figure out what this number is in decimal. So 1.1001 times 2 to the third. This is equal to, if I move this over, 1, 2, 3. So 1100.1. And do is first of all figure out what the whole part of the number is, and then I'll figure out the fractional part. So the whole part of the number, I have 2 to the third plus 2 squared, and this is equal to 12. So I have 12 for the whole part of the number, and then the 0.1, what I'm going to do is take, this is in the -1 space, so I'm going to take 2 to the -1 is equal to 0.5. So then I just combine these. So this 1100.1 is equal to 12.5.